All right, so here we have our end of unit guide looking at exponents and logarithms. So I'm going to go through pretty quickly, and please let me know if there's anything that you want more explanation on. So the first one here, we've got an equation, we've got our graph, and the key thing when you look at the graph is that the y-axis is measured in thousands. So if I'm going to use the graph to determine when it reaches 100,000, that means I'm looking at y equals 100 on the graph. So I scoot over from y equals 100 until I hit my curve, and then I go down from there. And that looks like, I don't know, x is about 4.2. You could say 4.3. You could even say 4.1. I'm not going to take points off. Just don't say 4.9. It's definitely closer to 4 than it is to 5. And part B says, explain why log base 2 of 20 also tells us. And that's just seems a little weird because there's no 20 involved in this problem. I see a base of 2, but I don't see a 20. It says that when the population will reach 100,000. So I can take the population of 100,000 and replace P of H with 100,000, which gives me this equation right here. Now this still doesn't involve the number 20. So I'm going to try to get H by itself, because the question asks when something will happen. So the opposite of times 5,000 is divide by 5,000. Turns out that 5,000 goes into 100,000 20 times. I used division to cancel multiplication. Now I'm going to use log base 2 to cancel the base of 2. And I get log base 2 of 20 is equal to h. This is the exact amount of time it takes for the population to reach 100,000, and we know from our graph that it's about 4.3-ish, because that's right below the y value of 100. All right, next one here. Explain why natural log of 4 is greater than 1 but is less than 2. The key thing to remember here is that natural log means log with the base of e, and that e is about 2.7. So I know, for example, that 2.7 to the first power is 2.7, and I know that 2.7 to the second power, well, I can't really, I can do 2.7 times itself with a decent amount of work, but I can also just compare it to 2 and 3. So, for example, what I know is that 2 squared is 4, and that's smaller than 2.7 squared, right? 2.7 is bigger than 2, so 2.7 squared is bigger than 2 squared, but it's also smaller than 3 squared. So what I know is that the e to the first power is about 2.7, and e to the second power is bigger than 4. So if it asks me about the natural log of 4, I know that that has to be smaller than 2. I know it also has to be bigger than 1 because 4 is bigger than 2.7. Okay, that was just doing it without grabbing a calculator. You're also welcome to use a calculator and get e to the second power. And this might be a little bit more of a clear way to explain this. E to the first power is about 2.7. E to the second power is about 7.4. And 4 is in between, not equal to, in between 2.7 and 7.4. That's fine. Okay, now let's put the expressions in order from least to greatest. Let's see here. There's a couple that are nice whole numbers, like log base 5 of 25 is 2. Log base 10 of 1,000 is 3, because 5 to the second power is 25, 10 to the third power is 1,000. I know log base 2 of 5 is a little bit bigger than 2, because log base 2 of 4 is exactly 2. So 5 is a little bit bigger. So I'm going to say 2 point, I'm just going to say 2.1. It might not be really 2.1. I'm just writing down it's a little bit bigger than 2. I know that log base 3 of 5 is bigger than 1 because log base 3 of 3 would be 1, but it's smaller than 2. So I'm just going to write like 1.2 here. And log base 2 of 11 is bigger than 3 because 2 to the third is 8. So I'm going to say 2.3. And so then we can put them in order. So this is the smallest, and then the second, and then the third, and then the fourth, and then the fifth. You can obviously also use a calculator. Okay, match each equation with a graph that represents it. So these are all logarithm equations here. And so what I'm going to do is just look for some values here. So all that's different is how quickly they grow. And if I make a XY table here for f of x, when I go log base 2 of 2, I get an answer of 1. Log base 2 of 4, I get an answer of 2. Log base 2 of 8, I get an answer of 3. This is just an exponential table written backwards. I'm going to switch colors on the next one. Now these are the powers of 10. So I go 10, 100, 1,000. 1, 2, 3. So what I want you to notice is that when I'm looking at a log, the bigger that the base is, the further to the right I need to move in order to go up by 1. So if I have a big base, I actually need to move further to the right in order to go up by 1. If you look at the blue graph, that's actually a nice coincidence. This one right here lines up here, 100, 2, all the way over to 1,000, 3. This one right here has to be D. Then after 10, the next biggest one is 5. So I know I can match C with the base of 5. And you can kind of eyeball it that when I'm at a value of about 125 here, I know this has to be 125, 3, for example. I know that this one right here needs to be 25, 2. Then the other two, what you need to know is that natural log means base of E, and that's bigger than 2. So this one is B. And then the last one is A. I actually got a lot of the colors right, just by dumb luck. That's pretty cool. Sweet. All right, moving along. Solve without using a calculator. Some solutions may need to be used with log notation. Here, I can just do log base 10 of both sides. That leaves me with n minus 3 is 1. Add 3. So n is equal to 4. On part B, to get rid of a half, I can multiply by 2. So 10 to the x is 0.1. Can do log base 10 of both sides. This one, honestly, I'm going to be okay with you leaving your answer as log base 10 is 0.1. If you want, you can go a step further because 0.1 is 1/10. So that actually comes out to be -1. You divide it by a 10. Okay, part C. Take log base 10 of each side because log cancels the base. So I have 1/3 t equals 2 because the power of 10 that makes 100 is 2. Multiply by 3, and you get t equals 6. Last one, log base 10 of both sides. It cancels out the left side, but doesn't cancel out the right side, and 48 is not a nice power of 10. So I'll just say 2x is log base 10 of 48, and then I'll divide by 2. Dividing by 2, you might think this is cheating, but you can literally just write log base 10 of 48 all divided by 2, or if you want to write 1/2 log base 10 of 48, that's fine too. So there you go. Again, Ask questions if you want me to do more problems like any of these. I'm just going kind of quick. All right, here Tyler is being clever. Using the fact that 2 to the 10th is 1024, Tyler estimates that 2 to the 20th is about a million. How did he get that? Well, 2 to the 20th is equal to 2 to the 10 times 2. There's nothing really revolutionary going on there. But that means that it's 2 to the 10th squared, because you can do a power raised to a power. And what Tyler's saying is that the inside piece is 1024, which is like kind of close to 1,000, which is equal to a million. So, okay, Tyler, sure, 2 to the 20 is about a million, I guess. It's bigger than a million, but it's kind of close to a million. Now let's think, is log base 2 of a million about 20? Well, yeah, I mean, if 2 to the 20 is about a million, then we keep the base the same and switch the other two pieces, and we get something that's about the same. So that's some pretty good estimation right there. For each logarithmic equation, write an equivalent exponential form. This one's just switching between logs and exponents. Here we have a base of e on all of these. It's just switching it around to the other format. Nothing really too fancy. So on each of these problems, what I imagine doing is putting an e underneath both sides of the problem. And just like always, bases and logs cancel each other out. And so you've switched between the two versions. All right, making good progress here. We've got some companies, F and G. We know that the y coordinate is 215. All right, cool. So we know that this right here is something, comma, 215.7. Okay, the intersection tells us where the revenues grow by the same factor. Nope, that is not true. They don't grow by the same factor because they have different slopes, which is not technically the correct word, but they have different growth rates. The intersection tells us whether they have the same revenue. That is correct. At the intersection, F is greater than T. Nope. They are equal at the intersection. At the intersection, they both equal to 215.7. That's what it means to intersect. We need to know both expressions to find the value of T at the intersection. That is not quite correct. Not quite. All we really need is one of the expressions. If we have one expression, we can set it equal to 215.7, and we can solve it. And because we already know the other piece of information, that they're equal at that point, knowing one expression is good enough. It's kind of a tricky question, honestly. If we know at least one, we can calculate. That's exactly it. We need to know at least one. We could also estimate it just with the graph. Not 10, maybe 12, 11. So it's going to be something around 11. Okay. The half-life of nickel, 63, is 100 years. An artifact will lose a quarter of that substance in 50 years. Do I agree with that statement? I do not agree with that statement. If the half-life is 100 years, that means that when the time is, let's just say we have a time here, and then this is the nickel. If we started out with 100%, that would be at time 0. And then if we get to time 100, we will have 50. But that does not mean that at 50, that would be 75. This right here is thinking of it linearly. We are not going down in a straight line. The reason we're not going down in a straight line is because that would mean that this is true, that we have 25, and then we have 0. That is not true. That's not how Half-Life works. The way that Half-Life really works is like this. You have 100%, then you have 50%. You know, put a little percent symbol next to it. Then after 200 years, you have 25%. And then after 300 years, you have 12.5%. So it cannot be the way that the red graph is. That's thinking about it linearly. It is not changing by that rate. If you want to know what's in between here, what you can do is take the square root of half. Because if it goes down by a half for 100 years, then it goes down by the square root of a half each time in between. The square root of a half is about 0.707, so that means we'd have about 70.7%. It needs to go down by more in the first chunk, like that. You see how the curve will go down by more initially, and then it'll flatten out. That's how exponential curves work. So that's why this drop is almost 30%, 30%, and then this drop looks like 20% because you have less left over. All right, scooting right along. We're on the last page. Cool. So now we've got bacteria. Sweet. So bacteria, it was measured, since it was measured to be 1,000, can be represented by the equation d equals log base 2 of p. Okay, you're probably more familiar with exponential equations, so I'm going to just raise both sides to the 2. Use a base of 2, I should say. So 2 to the d is equal to p. And usually when we write our exponential equations, we write it as something times number to the power. And if there's nothing there, it's implied to be 1. So now we're in kind of our normal exponential way. So every day, the population grows by a factor of 2. Yep, that checks out. The equation also, p equals 2 to the d, okay, I already got that, also defines it, nails it. The population reaches 7,000 after log base 2 of 7,000 days. Now that's close, but we got to remember that we're measuring p in terms of thousands. So it actually would only take log base 2 of 7 days. So this one is wrong. They did not do it right. Log base 2 of 10 tells when the population reaches 10,000. That time they did the units right. The equation d equals log base 2 of p is a logarithmic function. Sure, I mean, that's just like a vocab word. The equation 7 equals log base 2 of 128 reaches 128,000 in 7 days. Absolutely correct. There we go. So lots of correct statements right there. Okay. Respond to each question. What value of 2 would make this equation true? Well, the base is 2. That's the value of t. I know it's bigger than 2 and smaller than 3. I could grab a calculator to make it come out exactly. Between which two whole numbers? Oh, I just said that. How do I know it's bigger than 2? Because log base 2 of 4 is equal to 2. How do I know it's smaller than 3? Because log base 2 of 8 is equal to 3. So 2 squared is 4. That's smaller than 6. 2 to the third is 8. That's bigger than 6. All right. Last but not least, Andre says this. Andre is not right, although he's not that wrong. But if you think about the half-life example, you can't think about it linearly. It's not that it's halfway in between on a straight line. It has to curve along with it. Log base 10 of 55, if you type it into your calculator, turns out to be about 1.74. So he's not right because he's thinking of it like a straight line. If you think about going between 10 and 100 on a straight line, Andre's thinking, okay, there's 55. But if we're going between 10 and 100 exponentially, you'll notice that it actually curves and works at a different rate. Okay, and so it's not going to be 1.5. It's going to take a little bit longer to get there. So the 1.5 is a linear estimate, whereas exponentially it's going to get there in a little bit later. All right, so thanks for watching. Let me know what you need help with. Happy to help out.